In this video, we will do a conditional probability word problem. So I want to begin by recalling our formula for the conditional probability. The probability that A occurs given that B occurs. So we could write this as the probability of A intersection B divided by the probability of B, because we're given the condition that B has to occur. And that's why I remember that. That's the part. B has to be on the denominator. Okay. I can also write this in a simplified way if we have equally likely outcomes. So with equally likely outcomes, and we saw this when we first talked about conditional probability, we could write this as simply the number of elements in the intersection of A and B divided by the number of elements in the set B. Alrighty, so that said, let's do an example. Alright, so this example says that a university has 5,500 returning students and 1,800 new students. 1,600 of the new students live on campus, whereas 2,000 of the returning students live on campus. A randomly selected student lives on campus. What is the probability that they are a new student? Sorry, I was missing a Y there. All right, so to get us started, let's label some of these events. So one of the things it talks about is whether a student is a returning student or a new student. So let's have R be the event that a student is returning, is a returning student. And let's let N be the event that a student is new. And then we also have this matter of whether the student lives on campus or they don't. So maybe let's let C be the event that they live, a student lives on campus. And then maybe I could call D the event that a student doesn't live on campus. If I wanted to, I could also notice that D, I could also write this as just C complement. So if that was easier and I didn't want to create a new label, I could have also just called this C complement. Alrighty, so that said, what probability are we trying to find? So our goal here is to find the probability. Let's see, well, it tells us that a randomly selected student lives on campus. In other words, we're given that they live on campus. So we are given that they live on campus, and then it asks, well, what's the probability that they happen to be a new student? In other words, what's the probability that they are new, given that they live on campus? So with our labels, this is asking for the probability of N, given that C occurs. So let's get into how we would find this. Alrighty, so I'm going to zoom it out a little bit here to give myself some room to write while I can still look at the problem. So I'm going to talk about a solution to this in two ways. So solution one will involve just using the conditional probability formula. Probability formula. And then later we'll talk about, well, how can we do this with a tree diagram? Okay, so we are after the probability of N given that C occurs. So using our conditional probability formula, it's going to be the probability of N intersected with C divided by the probability of C. So whatever we're given that is what goes on the denominator, because we are limiting ourselves to those outcomes. Okay, so I need the probability that this person is new and they live on campus. Well, I know there are, let's see, it says 1,600 of the new students live on campus. So I know that it's going to be 1,600 over something. But to figure out how much I divide by, I need to know how many total students there are. So let's see, the problem, I see there's 1,500 returning students and 1,800 new ones. So I can use that to figure out the total. The total is going to be 5,500 plus 1,800, which is 7,300. So that is going to be the denominator of this fraction. We're finding the probability that a student is both new and they live on campus. So we got to count the number of new students who live on campus on top of the fraction, which is 1,600. And on the bottom, it's just the total number of students, which is 7,300. So next, let's get the probability on the denominator. The probability that a student lives on campus. Okay, so I know I'm going to divide by 7,300 because that is the total. So how many students live on campus? Well, there are 1,600 new ones who live on campus and 2,000 returning ones who live on campus. So we got to add those. So 1,600 plus 2,000. Okay, so let's simplify this. So if we simplify this a bit, for example, with 1,600 and 7,300, I can cancel a little bit. I could divide both of those by 100 and be left with 16 over 73. So I get 16 over 73. If I do the same type of thing on the bottom, first off, this becomes 3,600 over 7,300. And then after I cancel, it becomes 36 over 73. So now when I divide by this fraction, that's the same thing as multiplying by the reciprocal, 73 over 36. And now, this is nice because the 73's cancel. And I am left with 16 over 36. But those cancel a little bit too. I could divide each of those by 4 and be left with 4 up here. And 36 divided by 4 is 9. So we get 4 over 9. And that is our probability. So it simplified quite a bit. So you might have recognized that it would have been a little bit quicker because I have equally likely outcomes. So since we have equally likely outcomes, we could also simply say that this conditional probability of n given c is going to be equal to, and then count the number of elements in each of the sets in this fraction, as opposed to the probability. So the number of elements in n intersects c, divided by the number of elements in c. Well, what does this mean in this context? The numerator is now the number of students who are new and live on campus, which was 1,600. And the denominator is the number of students who are in C, the number of students who live on campus, which was 1,600 plus 2,000. So this is going to give us the same thing as before. It's 1,600 on top, 3,600 on the bottom. So I could simplify it just like I did before to get 4 over 9. And that's a little bit quicker. So when we do have equally likely outcomes, like we said on the top, we can use this bottom formula for conditional probability, rather than computing the probability on the top and the probability on the bottom. Both of them will work, just the bottom one was a little bit quicker. So next, let's solve this in another way, using tree diagrams. So for this, I want to give you the opportunity to try it first. So pause the video for 4 minutes and use a tree diagram to see if you can get the same answer. 4, 3, 2, 1, pause the video. Pause it and try this one for 4 minutes. Alrighty, so hopefully you've done that. Hopefully you've paused it and tried it for 4 minutes. It might not have been enough time to finish the question, but that's okay. I mostly care about that you thought about what the key ideas are, how we get started with the question, and hopefully make some progress with it. Okay, so I need a tree diagram, so let's write down our begin point. And there are a couple of things that we got to decide. There is the student type, so whether they're a new student or a returning student, and there's the matter of where they live. And once we do that, then we can write down the outcome, as well as the probability of that outcome occurring. Okay, so there are two events for student type. Either they are a returning student, R, or a new student, N. And then from each of these, either they live on campus, which is a C, or they don't live on campus, which is, we could write D, that's how we labeled it, or we could also do C complement for that. So even from here, I gotta put a D. Okay, and now let's write the outcome. So this is RC. Alrighty, so this is RC, and we have RD, NC, and ND. So now we're ready to label some probability. So how many students did we have who were returners? Well, the question said that there were 5,500 returning students. We figured out there were 7,300 total. So if we simplify this by dividing the top and the bottom by 100, this becomes 55 over 73. Okay, so in the same sort of way, for the number of new students, that was 18 over 73, if we simplify it. Because originally it would have been 1,800 over 7,300. Okay. So the question also tells us that, looking at the returning students, the number of them who decide to live on campus is 2,000. So we should have 2,000 out of the 5,500 returners living on campus, and this simplifies to 20 over 55. And then for new students, let's see, there were 1,600 of them who decided to live on campus out of 1,800 new students. So that would go here, and that simplifies to 16 over 18. All right, so now we can figure out these missing fractions. So the branch going from R to D, that has to be something that I add to 20 plus 55. Let's see, 20 over 55 added to some missing number needs to be equal to 1. So for this to work out, I could do a subtraction, or maybe I could see it in my head. This is going to be 35 over 55. Okay, let's label that. This is 35 over 55. And similarly, from N to D, this is going to be 2 over 18. So that when I add it to 16 over 18, it ends up giving me 1. Alrighty, so let's write down the probabilities. So for this first outcome, we're going to have 55 over 73 times, what is it, 20 over 55. The next one is 55 over 73 times 35 over 55. Then we got 18 over 73 times 16 over 18. The final one is 18 over 73 times 2 over 18. So now in each of these, we get some really nice cancellation, because the 55s on the bottom and the top will cancel away perfectly. And here the 18s will cancel away perfectly. So that'll leave us with 20 over 73, 35 over 73, 16 over 73, and 2 over 73. Okay, so we are now ready to write down our probability of n given that C occurs. So using the formula, this is the probability of n intersected with C over the probability of C. So the probability that n and C occur corresponds to this outcome, which has probability 16 over 73. So that's going to be my numerator here, 16 over 73. Let's highlight that in blue as well. And for the denominator, it's the probability that C occurs. So C occurs in two outcomes. It occurs in this outcome, 20 over 73 probability, as well as this outcome, which is 16 over 73 probability. So we got to add those probabilities. 20 over 73 plus 16 over 73. Okay, so this gives us 16 over 73 on top, over 36 over 73 on the bottom. And now if we do something really similar to what we did in solution 1 by multiplying by the reciprocal and simplifying, we will get the same answer, 4/9. So in terms of our goals for this section, we finished our first goal, which is to solve another conditional probability word problem. In the next video, we'll talk a bit about when do we use tree diagrams versus when do we use conditional probability formula to do something. Like in this example we did, it was a little bit quicker simply to use the conditional probability formula. The tree diagram worked, it was just a little bit longer to draw it, put in these probabilities, and simplify them to get the answer.